Okay. Hi, everyone. Thanks for coming to another Graphs and Matroids seminar. Today we have Tom Kelly, who's going to be talking about coloring hypergraphs of small codegree and a proof of the Erdős Faber Lovász conjecture. Go ahead, Tom.
Okay, thank you, Shayla. Thanks everyone for coming. I'm going to be speaking about joint work with colleagues at the University of Birmingham, Dongyip Kang, Daniela Kuhn, Abhishek Mathuku, and Derek Ostis. And I will just cut right to the chase this time and state the Erdős Faber Lovász conjecture for you. It's a very beautiful conjecture that's quite simple to state. There's a couple of different formulations, but I'm going to give you one in terms of graph coloring. So it states that if you have n complete graphs, each on at most n vertices, with the property that every pair of them shares at most one vertex, then the chromatic number of the union of these graphs is at most n. Okay, so the chromatic number of a graph is the minimum number of colors that you need to properly color it. And a proper coloring of a graph is an assignment of colors to its vertices, so that adjacent vertices are assigned different colors. So we can see this conjecture in action on this figure below. There's 4 complete graphs that are highlighted by the green. And indeed, they have at most 4 vertices, and every pair of them shares at most 1 vertex. So the conjecture predicts that you should be able to properly color them with at most 4 colors. And I've done so with red, blue, green, and orange. Okay, so this was a personal favorite of Paul Erdős. He often wrote about it and wrote that it was one of his 3 most favorite combinatorial problems. And he offered $500 for a solution. Erdős would often offer a small cash prize for problems that he particularly liked, and there were only a handful that he offered more than this for. And in the last year, we have proved the conjecture for all sufficiently large n. Now, today I also want to tell you about another result of ours that addresses a less well-known question of Erdős that's related to the Erdős Faber Lovász conjecture. So in 1977, Erdős asked, if you have n complete graphs, each on at most n vertices, again, just like in the Erdős Faber Lovász conjecture, but now with the property that every pair of them shares at most t vertices, then what is the maximum possible value of the chromatic number? So when t equals 1, then these graphs share at most 1 vertex pairwise. And so the Erdős Faber Lovász conjecture essentially says that the answer to this question is n. So what happens for larger n? Our result essentially answers the question when t is in the range of at least 2 and at most square root n, when it is sufficiently large. And it turns out that the answer is just t times n. So the theorem is that for t at least 2 and n sufficiently large, if you have these n complete graphs, as in the question above, then the chromatic number of their union is at most tn. And the reason that I'm saying that this essentially answers the question is because this result is best possible for infinitely many n. So in particular, for infinitely many k and n, and I'll tell you which those k are later, when n is equal to k squared plus 1 and t is at most k, there's a construction of these graphs g1 up to gn, such that the union of them has tn vertices and is itself complete. And so, of course, in that case, in order to properly color the union of these gi, since there's tn vertices and it's complete, we need at least tn colors. Okay. And for larger t, this regime is covered by a result of Horak and Tuza from 1990. They proved this general bound that holds for any t, that the chromatic number of the union of n complete graphs on most n vertices is at most n to the 3/2. Yeah, so it doesn't matter what t is, but when t is at least square root n, this construction from our theorem gives an example that where the chromatic number of the union of graphs is essentially also n to the 3/2, plus or minus some lower order terms. Okay, I'd like to point out that combining this result with the one from the previous slide, this theorem will actually hold for t at least 1. The case t at least equal to 1 is the Erdős-Faber Lovász conjecture. But I have that for t at least 2 to emphasize that this is a different result from a more recent paper, and it has a different proof. And so throughout the course of the talk, I'll tell you about some of the differences. Okay, so I think those conjectures are very beautiful questions, but that formulation in terms of graph coloring is a bit deceptive. And I think actually the correct way to think about these problems is as a problem about edge coloring hypergraphs. So that's what I'll tell you about next. So a matching, first off, in a graph or a hypergraph is just a set of disjoint edges. And a proper edge coloring now, coloring the edges instead of the vertices, is an assignment of colors to the edges so that no two edges of the same color share a vertex. And so you can see this is a proper edge coloring of the Peterson graph on the left. And on the right, this is a hypergraph that's also properly edge colored with 3 colors. Okay, so a hypergraph, if you don't know, like a graph, it's formally a pair consisting of a set of vertices and edges, where the edges are subsets of the vertices, but in hypergraphs, they're allowed to have any size. So this is a hypergraph where the edges have size 3. And this pair of red edges is a matching, as is this pair of blue edges and this pair of green edges. And so altogether, this proper edge coloring with 3 colors gives us a decomposition of this hypergraph into matchings, and that holds more generally. Okay, and finally, the Kematic Index is a useful notion. It's the minimum number of colors that we need to properly edge color a graph. So analogously to the chromatic number, but in the edge coloring setting. So the Peterson graph has Kematic Index 4. It's clearly at most 4 because I've had this proper edge coloring. And you can work out for yourself that it's not properly edge colorable with 3 colors. Okay. Now for graphs, the study of matchings and also the study of edge colorings is a very classic topic, and it's also very well understood. So in particular for graphs, we have Vizings Theorem, which essentially says that the chromatic index of any graph is always one of the most 2 values. It's either the maximum degree or the maximum degree plus 1. So the degree is the number of edges that contain a vertex. And that's clear, the maximum degree of a graph is clearly a lower bound for the chromatic index. So for example, in the Peterson graph, every vertex has degree 3. And just to color the edges incident to any vertex, we need at least 3 colors. And Vizings Theorem says that we always will only need at most 1 more color. Now, it's natural to wonder if Vizings Theorem extends to hypergraphs, and it doesn't, and we'll see. But this is kind of how you get to the Erdős-Faber Lovász conjecture. So in general, matchings and edge colorings are a lot more complicated for hypergraphs. A simple way to illustrate this point is that 3-dimensional matching, which is a special case of the problem of determining the size of a maximum matching in a hypergraph, the complexity problem, is one of Karp's original NP-complete problems. Whereas for graphs, we can solve it in polynomial time. And so unless you believe that P equals NP, we don't expect any nice characterization of hypergraphs with large matchings. But that doesn't stop us. In general, it's a very interesting question to ask which hypergraphs have large matchings and which ones have small chromatic index. Okay, so I want to go over some basics about hypergraphs before moving on to the Erdős-Faber Lovász conjecture again. So in this talk, I'm actually going to allow hypergraphs to have repeated edges. So for example, this multigraph on the left, I'm going to consider a hypergraph. Yeah, so we have, for example, this red and blue edge, they have the same set of ends. So I'll consider that a hypergraph. But I'm not going to allow edges to have size 1 in this talk. Edges of size 1 are just a nuisance from the perspective of coloring. So unless I say otherwise, assume hypergraphs don't have size 1 edges. And there are a couple important terms for us. The codegree of a hypergraph is the maximum number of edges that contains any given pair of vertices. So for example, in this multigraph on the left, you can see that every pair of vertices actually is contained in 2 edges. And so the codegree of this guy is 2. Now a hypergraph is linear if every pair of vertices is contained in at most 1 edge. And in other words, a hypergraph is linear if it has codegree 1 or codegree most 1. So the example from the previous slide, which is on the right here, is an example of a linear hypergraph. You can look at all the pairs of vertices and check that indeed at most one edge contains them. Finally, a hypergraph is K uniform if every edge has size K. So from this perspective, multigraphs are just a set of 2 uniform hypergraphs, since we're allowing repeated edges. And graphs are just the 2 uniform linear hypergraphs. So I said Vizings theorem doesn't extend to hypergraphs. With this definition of hypergraphs, this example on the left is already a counterexample. We know Vizings theorem doesn't extend to multigraphs. This is a multigraph that has maximum degree 4, but it has Kematic Index 6 because it has 6 edges and they all need distinct colors. So you might complain, well, it's a multigraph. It's not linear like graphs are. So this is I think how you get to Erdős Lovász conjecture. So the conjecture states that if you have an n vertex linear hypergraph, then the Chromatic Index is the most n. So you can properly edge color it with the most n colors. And you can think of this as like a test case for a Vizings theorem for hypergraphs, because linear hypergraphs have maximum degree at most n minus 1. And graphs have Chromatic Index at most n by Vizings theorem. So I'd like to explain the connection between this formulation of Vizings theorem and, of the Erdős Lovász conjecture, and the one that I gave you on the very first slide, which is repeated at the bottom. So I'm claiming they're equivalent. To see that the bottom formulation implies the top, we need to consider the line graph, the notion of a line graph. So if for example, we have this hypergraph on the left, which is linear, the hypergraph on the right is the graph on the right is this line graph. The line graph has vertices, has 1 vertex for each edge of the original. And you can see for the correspondence, for example, with the colors. This blue vertex corresponds to this size 3 edge, and this bottom blue vertex corresponds to this edge. And then edges from the original hypergraph that share a vertex are adjacent in the line graph. In other words, for every vertex of the original graph, we add a complete graph to the line graph. And so the complete graphs are kind of illustrated by the figure on the right. And so it turns out that if you start with an n-vertex linear hypergraph and take the line graph, what you get is a graph which is the union of n complete graphs, and each will have at most n vertices, and every pair will share at most 1 vertex. And so the bottom formulation will imply, if true, that the line graph has Chromatic number at most n, and you can use that to then properly edge color the edges of the original. Now to see that the reverse direction holds, we need the notion of hypergraph duality. So here, if we start with n complete graphs, like in the bottom formulation, we construct some kind of auxiliary hypergraph, like on the right, where each complete graph corresponds to a hyperedge on the same set of vertices. And then we take what's called the dual, where edges become vertices and vertices become edges. Then we get the figure on the left. And then we take the line graph and we get back to what we started. So we have this kind of cyclical thing. And if we apply the Erdős Lovász conjecture to the dual of this auxiliary hypergraph, then since hypergraph duality preserves linearity, we can indeed apply the EFL conjecture and get a proper edge coloring with the most n colors, which will then transfer over to the line graph and give us a proper vertex coloring with the most n colors. Okay, so the details of that aren't too important, but these 2 notions, line graph and hypergraph duality, are essentially the reason why the top formulation is equivalent to the bottom. So now let's see what happens when we apply the same reasoning to the Erdős question from the second slide. So this is the question from the second slide. We have n complete graphs, each on the most n vertices, and every pair shares the most t vertices now. And we want to know what's the max possible value of the Kematic number of the union. So let's say we start with this graph in the middle, which is the union of 3 complete graphs. We do the same thing where we replace each one of these complete graphs with a hyperedge in some kind of auxiliary hypergraph, like this one on the right, and then we take the dual. It turns out that what we'll get is a hypergraph where the max degree of the hypergraph is equal to the maximum size of one of these cliques from the original. So in particular, in this example, this top vertex has max degree, it has degree 4. And you can see it's incident to the red, blue, purple, and orange edges. And this is corresponding to this clique of size 4 on the top that has, again, a red, blue, purple, and orange edge. Okay, so the max size of one of these cliques in the original formulation becomes the max degree of the hypergraph that we get in the dual formulation. And that's this blue condition. And now this green condition that every pair shares the most t vertices corresponds to the codegree of the dual. So here, the codegree of this hypergraph on the left is 2. For example, we have, again, this red and blue edge that are repeated, certifying that the codegree is 2. And these 2 edges correspond to, for example, these 2 vertices, which are in the intersection of 2 of the complete graphs. So that this top one and this bottom left one, they intersect in the red and blue. They intersect in a set of size 2, and that's the codegree of H. Okay, so what we get is that this question of Erdős is equivalent to this thing at the top, that if you have an n vertex hypergraph that has maximum degree of most n and codegree of most t, then what's the maximum possible Kematic index? Because now we're edge coloring instead of vertex coloring. Now, of course, as before, the case t equals 1 of this question corresponds to the Erdős-Faber-Lovász conjecture. But you notice that we have this this condition that we have maximum degree of most n that wasn't appearing in the Erdős-Faber-Lovász conjecture. But it's somewhat redundant in the case t equals 1, because linear hypergraphs, since I'm not allowing size 1 edges, linear hypergraphs have maximum degree less than n. But for t larger than 1, this hypothesis can come into play. In fact, in this example, this is a 3 vertex hypergraph, but it actually has a vertex of degree 4. So it has codegree 2, 3 vertices, and maximum degree 4. So it actually doesn't really fall under this question unless you add an extra vertex or something. Okay, so the reason that I think that this dual formulation is kind of the proper way to think about the Erdős conjecture and also this more general question of Erdős is because it's easier to understand the extremal examples. So for the Erdős-Faber-Lovász conjecture, there are kind of 3 main families of extremal examples. On the left here, I have the Fano plane, and this is the finite projective plane of order 2. In general, the finite projective plane of order k is a k+1 uniform hypergraph that's linear and intersecting, which means that every pair of edges intersects in a vertex. And the number of vertices and edges is the same. It's equal to k squared plus k plus 1. And you might recognize this from the first slide. But so the reason that this is an extremal example is because since it's intersecting, we need to give every edge a distinct color in a proper edge coloring. And since it has the same number of edges as vertices, then if it has n vertices, then we need at least n colors. Okay, so that's the first example. The second example is what's sometimes called the degenerate plane, or also called the near pencil. And that one's in the middle. It's extremal for the same reasons as the finite projective plane. It's an intersecting hypergraph that's linear, that has the same number of vertices as edges. But the construction is much more trivial. You just take a single edge of size n minus 1, which leaves out one vertex, and then you add all of the size 2 edges between that vertex and every other vertex. And it's fairly easy to see that that is indeed intersecting and linear. And lastly, another extremal example is simply the complete graph on an odd number of vertices. So if you were to properly edge color the complete graph with less than, well, if your complete graph has n vertices and you properly edge color it with less than n colors, because every vertex has degree n minus 1, every color class would be a perfect match, which is only possible when n is even. So you can't do it when n is odd. Okay, so now what are the extremal examples? So what are the extremal examples for this more general question of Erdős? Since Erdős didn't actually pose a conjecture, he just asked a question: what's the maximum possible value of the Kematic number, the Kematic index, what have you? I will substitute in this conjecture that I'm going to refer to as the TEFL conjecture, which states that if you have an n-vertex hypergraph that has codegree T and max degree at most n, then it has Kematic index in most Tn. And so I claim that proving this TEFL conjecture is essentially the same as answering the question of Erdős. And the reason being is because that this is, if true, best possible, as certified by what we call T-fold projective planes. So to attain a T-fold projective plane, you just replace each edge in the projective plane with T repeated edges. So on the left here, for example, the order 1 projective plane actually turns out to just be a triangle. And so the threefold order 1 projective plane is this thing on the left, where I have 3 parallel edges for each edge of the triangle. And on the right, we just have the Fano plane again. I didn't want to draw repeated edges in the Fano, so let's just say that this is the one-fold Fano plane, okay? But you could imagine repeating the edges of this hypergraph. And this is this construction gives you an extremal example whenever T is at most K. So the reason being that the T-fold projective plane of order K on n vertices where n is K squared plus K plus 1 has Tn edges, okay? Just the one-fold projective planes have n edges, and then when you take the T-fold version, you have to multiply it by the number of edges by T. And it's still an intersecting hypergraph when you repeat the edges. So for the same reason, you need to assign every edge a distinct color in the proper edge coloring, and there's T edges. And it satisfies the hypotheses of the conjecture because it has codegree T. So the one-fold one is linear, and then we replace each edge with T copies, so the codegree becomes T. And the maximum degree is equal to T times K plus 1. And this is at most n when T is at most K. So this is where the thing from the second slide comes in, how we answer the question when T is at most screwed in. So what happens is we start with the, if we start with the one-fold projective plane of order K, then the max degree is K plus 1, and we can duplicate edges iteratively up until the point where T is essentially square root n, and then at that point, the maximum degree will become larger than n. Okay. So I already told you about some of our results at the beginning, but now I want to back up and give you a bit more background on these problems and tell you about our results in a bit more detail. So again, here's the Erdős-Faber-Lovász conjecture. And first, it's interesting to observe that a direct approach where you just color the edges greedily in order of their size, starting with the large edges first and ending with the size 2 edges, will yield a proper edge coloring of any linear hypergraph on n vertices that uses at most 2 n colors. And Cheng and Lawler in 1989 used a similar argument that was a bit more clever to reduce this down to 3 n over 2. Now, a different approach to the conjecture is to prove it for relaxed parameters. So De Bruijn and Erdős in 1948 proved a result that says that the EFL conjecture is true for intersecting hypergraphs, which in particular means that if we take the line graph of an intersecting hypergraph, then if we take the line graph of an intersecting hypergraph on take the line graph of an invertex linear hypergraph, then it doesn't have a clique of size larger than it. Okay. Now, Seymour generalized this in 1982 by proving that every invertex linear hypergraph has a matching of size at least the number of edges divided by n. And this is again a relaxation of the EFL conjecture, because anytime you have a proper edge coloring of a hypergraph with n colors, the color classes form matchings, and the average size of those matchings would be at least this. So in particular, the largest one of those matchings would also be at least this. And then finally, Kahn and Seymour generalized this further in 1992 by proving a fractional version of the EFL conjecture. Now, I think the most interesting results for the conjecture are the following two that use a probabilistic approach to color the graph. So this result of Faber and Harris from 2019 implies that the EFL conjecture is true if all of the edges have size at least 3 and have size at most some small absolute constant times square root n. And note that this range of the edge sizes is forbidding the hypergraph from being too close to one of the extremal examples, because the complete graphs, obviously, at every edge has size 2, which is not in this range. And the projective planes and the degenerate planes have edges of size larger than c times square root n. But in excluding those, this result implies that the conjecture is true. And Kahn in 1992 proved that he proved an asymptotic version of the conjecture. So he proved that as n tends to infinity, the Kematic Index tends to n. It's at most n plus little o of n. Now, both of these results, as I mentioned, are proved with a probabilistic approach. In particular, they use a generalization of the Pippinger-Spencer theorem to list coloring that was proved by Kahn in the early 90s. So the Pippinger-Spencer theorem, just stated for the ordinary edge coloring, it states that if you have a hypergraph that has bounded edge sizes, maximum degree at most delta, and codegree little o of delta, then it has chromatic index at most delta plus little o of delta. Now, already this result has some important corollaries for both the EFL conjecture and the TEFL conjecture for hypergraphs of bounded edge sizes. So if the edge sizes are bounded and they also have size at least 3, which is similar to the Faber and Harris result, then the Pippinger-Spencer theorem will imply that the chromatic index is at most n when n is large. Because a linear hypergraph where all of the edges have size at least 3 will have maximum degree at most n over 2. Now, as I said already, a linear hypergraph on n vertices will always have maximum degree at most n. So for linear hypergraphs with bounded edge sizes, the Pippinger-Spencer theorem also implies an asymptotic version of the EFL conjecture. So it's a weaker version of Kahn's result that for bounded edge sizes, the chromatic index is n plus little o of n. And then finally, the Pippinger-Spencer theorem actually implies the TEFL conjecture when t is at least 2 for hypergraphs with bounded edge sizes. Because recall, in the TEFL conjecture, we're allowed to use Tn colors. But in that conjecture, we were already imposing that the maximum degree was at most n. So the Pippinger-Spencer theorem says that we just need a bit more than n colors, which will be less than Tn when t is bigger than 1. So the Pippinger-Spencer theorem is quite good for the TEFL conjecture for t at least 2. Okay, so now I'll tell you about our results. So as I said, we proved the EFL conjecture holds for sufficiently large n, which implies that this edge coloring formulation holds for all but finitely many hypergraphs. So for sufficiently large n, every n-vertex linear hypergraph has chromatic index at most n. We also proved a stability result that Kahn predicted. So the result says that if you have delta at least 0, then for some sigma at least 0 and n sufficiently large, the following holds. For an n-vertex linear hypergraph with 2 properties, one, the max degree is bounded away from n, and two, the number of edges of size roughly square root n is also bounded away from n. Then the chromatic index is bounded away from n, but this time by sigma n. So it's a stability result because instead of using n colors, we're using a bit less. And the hypotheses here say that the hypergraph is not too close to one of the extremal examples. In particular, the projective planes essentially have n edges of size square root n. Okay, so this condition is saying that it's far from being the projective plane. Okay, so now here's what we prove for the TEFL conjecture for T at least 2. So we confirmed the conjecture for all but finitely limiting hypergraphs, but we actually proved something that's stronger in 3 respects. So we proved that for all epsilon at least 0 and n sufficiently large, if you have a hypergraph on n vertices with codegree most t, and now we allow maximum degree to be at most 1 minus epsilon tn instead of just n, then the list chromatic index is at most tn. So this is stronger in 2 respects in that we have a relaxed maximum degree assumption, and it also holds for list coloring. But we go further than that. We actually characterize the extremal examples. So if equality holds here, then we actually can say that the hypergraph is in fact a t-fold projective plane. So I stated this for list coloring, but this also holds if you replace the list chromatic index with the chromatic index. Also, interestingly, this result holds for t equal to 1. But for t equal to 1, it does not imply the result from the previous slide, because for t equal 1, the hypothesis of this theorem is that the maximum degree is at most 1 minus epsilon. But nevertheless, I think this is interesting because for the case t equals 1, this theorem says that if you bound the maximum degree away from n, like in the EFL conjecture, then we can prove the EFL conjecture, but we can also prove that it holds for list coloring. And again, we can say that the only extremal example with maximum degree bounded away from n is the projective plane. Okay. And then we also were able to generalize the stability result from the previous slide for any t. And we also can generalize the De Bruijn-Erdős theorem. So this is a generalization of the De Bruijn-Erdős theorem on the bottom. It says that if you have an invertex hypergraph that is intersecting, that has codegree at most t, then it has at most tn edges. And moreover, if equality holds, then the hypergraph is either a t-fold projective plane or it's a t-fold near pencil. So here we don't have any condition about the maximum degree. We just know that the hypergraph is intersecting, and we can bound the number of edges. And we can say that if equality holds, that it's one of these 2 examples. And actually, so I think this is a nice generalization of the De Bruijn-Erdős theorem. It's not too challenging to prove. We actually need it to characterize the extremal examples for the theorem above. Because in this proof, we first proved that if equality holds here, then the hypergraph is intersecting. And then we deduce from this De Bruijn-Erdős theorem generalization that it has to be the t-fold projective plane because the t-fold near pencil has too large maximum degree. Okay. So now let me tell you a bit about the proof. Okay, so these are results from 2 different papers, but combining the results, you can get the following theorem. If you have an invertex hypergraph of maximum degree at most n and codegree at most t, that's sufficiently large n, the chromatic index is at most t. And so I want to give you some kind of a roadmap to the proof, and I will talk about how the proof is different in the cases t equal 1 and t greater than or equal to 2. In both cases, an important stepping stone is what I call the small edge case, which is when all of the edges are of bounded size. And this actually was already highlighted by Kahn in 1994, as being exactly that, an important stepping stone towards the conjecture. It captures a lot of the difficulties of the problem. Now for t greater than or equal to 2, as I said earlier, the Pippinger-Spencer theorem, proved via this nibble approach, actually already implies the TFL conjecture. It implies this result. So the small edge case for t at least 2 is if you're willing to assume the Pippinger-Spencer theorem is a black box, it's not too difficult. Of course, the Pippinger-Spencer theorem itself is a very nice result. And for t equal to 1, the Pippinger-Spencer theorem gives you an asymptotic version of the small edge case. So for t equal to 1, the Pippinger-Spencer theorem says that in the small edge case, you can use n plus little o of n colors. So the important task here is to get rid of this extra little o of n colors. And here we use some absorption ideas to reduce this case to a graph coloring problem. And I'll elaborate on that a bit later. The next important stepping stone is what we call the Ftp Extremal Case. And here FPP stands for finite projective plane, because this case includes when your hypergraph is the projective plane or close to it. So this is the case when all of the edges have size at least 1 minus delta squared n for some small delta. And here it's a few page argument. It's a bit delicate. I won't go into the details on it, but I will mention that for t at least 2, there are some difficulties in generalizing it, but we were able to do that. And then in the second paper, we additionally proved that if the chromatic index of the hypergraph is less than Tn in this case, we proved that the chromatic index is less than Tn in this case, unless the hypergraph is intersecting. So this is how we're able to characterize the extremal example in the t greater than or equal to 2 case. Now the third case contains the second one as a special case. It's the large edge case, when all of the edges have size at least r for some absolute constant r. And here, I mentioned earlier this direct approach of coloring edges greedily in order of their size. This actually works particularly well when all of the edges are large. When all of the edges have size at least r, this strategy will use at most 1 plus 2 over r times Tn colors. And again, this is easier to prove this is trivial for t equal 1 and a bit more difficult to prove for larger t, but it does indeed work. And an important tool to prove the large edge case is what we call the reordering lemma, where we essentially try to rearrange this ordering. We start with the ordering by size and we try to rearrange it. And if we can find an ordering where the greedy coloring uses less than Tn colors, then we're of course happy. And otherwise, we find some highly structured subset of the hypergraph that is essentially all of the hypergraph and either looks like a projective plane or it has this additional property. I'll say something about that later. Okay, so finally, having done these 3 important special cases, we of course need to figure out a way to prove the theorem by merging them somehow. And the strategy in doing so is to first color the large edges, so we're using the same argument as in the large edge case, but we need to do some extra work to help ourselves out later on when we go to color the small edges. And then we color the small edges in a way that's compatible with the coloring of the large edges. And that's the same argument as the small edge case, but again, with extra work because we need to avoid conflicts with the large edges. So I won't go into the details on that. I will mention that for this to work, the stability result that I mentioned is actually a key ingredient. We do need that in the non-FPP extremal case, you can use fewer colors. And now, I'd also like to remark that if you're genuinely interested in learning how the proof works, then we've written a survey on the nibble method that's on the archive that includes some parts of this roadmap as special cases. So in particular, the small edge case for t = 1, and the large edge case, in particular, the reordering lemma for t = 1. And so because we proved them separate from each other, we don't need to deal with these extra difficulties regarding merging the two cases. So the proof is a lot simpler. So if you want to understand the proof of the EFL conjecture, then understanding the two cases in isolation I think is very helpful. Okay, so now let me comment on some aspects of the proof. So this is, now imagine t = 1 and we have a hypergraph where all the edges have size either 2 or 3. So this is the small edge case, but actually with really the edges have size at least 3. Let's fix some small constants, gamma and epsilon, and let U be the set of vertices that have degree at least 1 minus epsilon times n. So we're separating out the high degree vertices, which are in U, and the low degree vertices, which are not in U. And this dichotomy here is important. So on one end of the spectrum, since all the edges have size, if all the edges containing this vertex have size 3, then it can have degree n over 2. On the one hand, this type of vertex is challenging to deal with because edges of size 3 are more challenging to deal with than graph edges. But on the other hand, we have more flexibility because just to color this local part, we only need n over 2 colors. And on the other end of the spectrum, a vertex of high degree will need almost all of the colors just to color the edges containing it, but it's more graph-like. In order to have high degree, it has to be contained in mostly graph edges. And so by separating out these high degree vertices U, we're kind of isolating some graph within the hypergraph that is somewhat dense, which is really a good setting for absorption. Okay, so we'd like to reduce this to Vizings theorem. The idea of this is that we'll partially color the hypergraph with a bit more than n over 2 colors in such a way that we color all the size 3 edges. And in doing so, we can't neglect the graph edges. We will also need to color nearly half of the graph edges to each vertex. And finally, we need to treat the vertices in U with special care. In particular, we need to ensure that every color class covers U. And this is what we call perfect coverage of U. So if we only cared about these first two properties, then the nibble method would work well. So with n over 2 plus gamma in colors, this random approach to coloring would succeed in coloring the size 3 edges and would also color nearly half of the graph edges at each vertex. But of course, it's not likely to cover every color class of U perfectly. And this is where absorption comes into play. In particular, we exploit the fact that the vertices in U have high degree, and we use some of their uncolored edges and we color them as well to get this perfect coverage property. And this is the absorption idea. Okay. Now, assuming that we have this Vizing reduction, well, then we can reduce it to Vizings theorem, right? So this is how it works. What we are left with is a graph that has max degree less than n minus k, because vertices in U started out with degree at most n minus 1, and because of this perfect coverage property, had k of the edges containing them get colored, which results in their degree being less than n minus k. And the vertices not in U had low degree to start, and we have roughly half of their edges containing them remaining, which is also at most n minus k. And so we just apply Vizing's theorem to what remains. We combine the two colorings, and we'll have used at most n colors in total. Okay, now unfortunately, this doesn't always work. It's not even possible to find a coloring with perfect coverage of U if, for example, our hypergraph is one of the extremal examples, if it's the complete graph on a non-number of vertices. So in this case, the set U would just be the set of all the vertices. And a coloring with perfect coverage of U would be one in which every color class is a perfect matching, but it doesn't have a perfect matching when n is off. So what we can do instead is find a coloring as in here, with kind of the next best thing, what we call nearly perfect coverage. And this will actually work if we allow ourselves one extra color. So you can apply the same Vizing reduction argument with this Vizing reduction with nearly perfect coverage instead of perfect coverage, and you get this result that the EFL conjecture holds in the small edge case with one additional color. And actually, this is what we wrote down a proof of in that survey that I mentioned before. So the proof is particularly streamlined if you give yourself one extra color, which I think is nice. And so we need additional ideas to get rid of that one extra color, but I won't go into the details today. I think in the interest of time, I'll skip this part about the large edges, and I will wrap up. So to summarize, we have this TEFL conjecture that says that if you have an n-vertex hypergraph with codegree T and max degree at most n, then it has chromatic index at most Tn. Okay, and so combining our results from the two different papers, we have this theorem which resolves this conjecture for sufficiently large n. So in particular, the case T equals 1 confirms the Erdős Lovász conjecture for all but finally many hypergraphs. And then for T at least 2, we have some additional results. So we can characterize the extremal examples. We can prove that the bounds hold for list coloring, and we can prove that it holds with a relaxed maximum degree assumption. And then in addition to this theorem, we have these stability results, and we have this generalization of the de Broglie average theorem. Okay, so I want to leave you with some open problems. In particular, I first want to pose the problem of characterizing the extremal examples for the EFL conjecture. So we've done it for the TEFL for T at least 2, but it's still open for T equal 1. So I gave you these 3 different families: the projective planes, the degenerate planes, and the complete graphs. And this should essentially be all of the extremal examples with some minor modifications, which I'll describe. So there's the notion of an overflow graph, which is a graph that has max degree delta and n vertices and has more than delta times the floor of n over 2 edges. And it's simple to prove that overflow graphs will always have chromatic index delta plus 1. So another reason that the complete graph on an odd number of vertices is extremal is that it's an overflow graph with maximum degree n minus 1. But there are other examples. So for example, this is K5 minus an edge, and it's still extremal. So it has 9 edges, and each color class is a matching that can have size at most 2. So if I were to use only 4 matchings to try to cover all of these edges, I would only be able to cover 8 out of the 9 edges. So it still requires 5 colors. And there's another modification of the degenerate plane where you replace the point of the pencil with a clique. And this will also give you an extremal example if that clique that you replace it with has odd size. So I think that this should be all of the extremal examples. So the conjecture is that if you have an n-vertex linear hypergraph with chromatic index n, then either H is one of these overflow graphs, or it contains one of these overflow graphs as a subgraph, which in particular means that the number of size 2 edges is at least n minus 1 squared over 2, and n is odd. Or it's just a finite projective plane, or it's one of these odd blow-ups of a degenerate plane. Okay. And our results on the TEFL paper imply that if the maximum degree is bounded away from n, then we do get this case. But of course, when the maximum degree is allowed to be n, or n minus 1, that's when these constructions show up. Okay. Now, another interesting open problem is this conjecture of Burch, Freddy, and Manuel. And this, if true, would actually be a proper generalization of Vizings theorem for linear hypergraphs. So it says that every linear hypergraph has chromatic index at most this quantity, which you can think of as the maximum over the vertices of the number of neighbors a vertex has plus 1. So for graphs, the number of neighbors a vertex has is the same as its degree, but that's different for hypergraphs. So for example, in this hypergraph on the left, this vertex has 4 neighbors, and you add 1 to it and you get 5. Another way to think about it is it's the max degree of the shadow graph plus 1, where you replace each one of these hyperedges with a complete graph. So this would imply Vizings theorem if true, because the number of neighbors in a hypergraph is, in a graph is the same as the maximum degree. And it also implies the EFL conjecture, because for linear hypergraphs, this quantity is always the most. I think that would be really nice. Another question is whether the EFL conjecture holds for list coloring, which was actually posed by Faber in 2017. So I've kind of been talking about list coloring without properly defining it in this talk. What this means is that if every edge has a list of colors that has size at least n, then you can properly color the hypergraph in such a way that every edge is assigned a color from its list. Lastly, here's a problem that looks like the EFL conjecture in some sense, because it says that if you have an n-vertex hypergraph that is intersecting now, rather than linear, then instead of decomposing it into matchings like in the EFL conjecture, you can decompose it into n subsets of edges, where each one has this kind of strong intersecting property, that every pair of edges in that subset intersects in at least 2 vertices. And I think an interesting aspect of this conjecture is that both this one and the EFL conjecture are implied by the de Bruijn-Erdős theorem for intersecting in linear hypergraphs. So in order for the EFL conjecture to hold for intersecting hypergraphs, you need the intersecting linear hypergraphs have at most n edges. And that's also the case for the restricted alignments conjecture. Okay, so I'll stop there. Thank you for listening.
Thank you so much, Tom. Let's do a round of applause if everyone can please unmute, and then I'll count to 3 and then we'll clap. 1, 2, 3. Awesome. All right, does anyone have any questions for Tom? If you do, you can just unmute and ask.
So what are the main new difficulties when trying to prove that first conjecture?
Reverse Freddy conjecture?
Yeah.
So, well, I guess, I mean, you could try to follow this roadmap to the proof, like I said, for the EFL conjecture. But, so it does hold asymptotically, first of all. Yes. I don't know, okay, let me back up. So the absorption ideas are a bit unclear in this setting. So in particular, we have the set U of high degree vertices. And as I said, in doing so, if we look at the graph edges, the size 2 edges that are incident to one of these U vertices, then what we get is a subgraph that is like kind of halfway dense. It has this chunk of this as its like dominating set of vertices that all have high degree almost n. And that really powers the absorption. Absorption works well in the dense setting. And we've kind of isolated this dense graph that we can do the absorption on. But in the Birch-Freddy manual conjecture, I mean, you could replace this this n with the max degree of the shadow, but what you get is no longer the resulting graph no longer is as dense. Like n could be much bigger than the max degree of the shadow, in which case we won't have a lot of the properties that we use for absorption. Like for example, two vertices in U, they have a lot of neighbors in common, for example, which might not be true in the setting of the Birch-Freddy manual conjecture. Yeah.
Any other questions? Maybe I'll end the recording there, and then we can have some informal discussion. Thanks again, Tom.